Hello, hello.
Hello.
Uh, my mic is connected to my webcam right now, not the correct mic. So let me try to fix the problem here really quick. For some reason it's connected to the wrong mic.
Oh,
Recording in progress.
Hello, hello. Let's see, did my mic change? Yes, it did change. Okay. Um, okay. Can you hear me clearly?
I can
yeah.
hear you, yeah.
Okay, okay. Let's get yeah. So, hey Madison, how are you?
I'm good. How are you?
I'm doing fine, doing fine.
Good.
Hey Wiley, uh, did you have any questions that you wanted to go over today? Like, what did Bio go over yesterday? Like, was it sword oxidation? Um, what were there
Not
anything else
really.
that he went over today?
Not really. Uh, you just talked about how you can stop either at the carboxylic acid or the aldehyde, depending on what oxygen you use. I have to
Right.
wait for tomorrow for his
Yeah.
next lecture.
Right. Like PCC, Jones, and the safer ones for oxidation reagents. Yeah,
Yeah,
we'll see for tomorrow.
yeah.
Let's see. Okay. Were there any questions or problems you wanted to go over today?
Do you have more practice?
Practice? Let's see. On alkenes, alcohols, we could see something. I think you're learning about alcohol, so let's pull up some alcohol practice.
I would say alkene alcohol practice as well, just like you going over that.
Okay, okay. Yeah, alkene alcohol practice. Hey, Lysia.
Hi.
Alkene alcohols. No, we went over this. Over this. Good neutral agent. So, oh, here we go. Okay, let's do this one. Okay. So for these oxidation of alcohols reactions, the reactant molecule is going to give us some functional group, and the reagent is going to give us some oxidizing agent. Let's go through this one by one. What product would you predict for part A reaction here? And before we can do that, we could also analyze what kind of
Oh,
functional group we have,
I
what type it is. So what functional group do you see present in the reactant and what type? Like, is it going to be
it's a tertiary alcohol.
tertiary alcohol, right?
I don't think it's gonna do anything because
Yeah.
it's fully like bonded, the carbon attached.
This carbon here is fully bonded. There's no hydrogen, so we can't exchange a hydrogen for an oxygen, so we cannot oxidize this tertiary alcohol. That's correct. Whenever you see chromium and a lot of oxygens, what type of oxidizing agent comes to mind?
Jones.
Jones reagent, yes. And when we have Jones reagent here reacting with this reactant, which functional group would be affected? This ketone or this aldehyde?
The aldehyde?
Yeah, the aldehyde. And what functional group would that aldehyde be converted into?
Oh, uh is it carboxylic acid?
Yes, carboxylic acid. And be careful here. We have to keep track of all the carbons. This carbonyl carbon right here of the aldehyde is going to be the carbonyl carbon of the carboxylic acid. So we're just gonna substitute that H with an OH like that. And to keep track of all the carbon atoms, we have 1, 2, 3, 4 carbon atoms. That's gonna be 1, 2, 3, 4 carbon atoms right there. Right. So this right here would be also Jones reagent because we have a lot of chromium and oxygens. So with this Jones reagent, what product would you expect from this reactant here?
Would it react to wait, no, this is 1, 2, 3. Would you get a ketone on the left and then on the right would be carboxylic acid?
Yep. We'd get a ketone on the left because that's a secondary alcohol. The one on the right is a primary alcohol. So we'd get a ketone on the left. And on the right, we would convert that primary alcohol into a carboxylic acid like that, right? Have you learned about hydrohalogenation of alcohols yet?
I believe so. Is it with the E2 mech?
Um,
Or
Depends
is it
on the type of alcohol and the
oh
temperature. Did BO give you like low temperature versus high temperature?
no.
No, okay. So I don't want to go over that reaction yet because the different professors will have different temperatures, which they consider high temperature or low temperature, and that would affect what reaction it is, like SN2,
Oh,
E2,
okay,
or
okay.
SN1, E1. Right.
Okay.
So before we move on to that, I'm gonna wait for what Bill says, and then I'll look at his notes and then create similar practice problems based on his material, so that I don't confuse you with
Okay.
the series or Liebens or any other professor's material. Right. Okay. Yeah. And I know Madison wanted to go over alkene. Oh, wait, Madison's from 8B, right? You're from 8B?
Yes.
Yes, so that's different than 118B and 128B. You're learning about carboxylic acids right now, right? Like in the derivatives?
I believe so. I can't remember if we like just barely touched on that in this last lecture.
Yeah. Um, let's see. Did you have any questions or practice problems you wanted to go over, or any like topics that you wanted me to go over and create similar practice for you?
I do. I'm trying to pull it up right now.
Okay. Oh yeah, I got your notes, Elysia, the annotated notes. They're so neat. What the heck? Did you take these
Oh,
during class or like
yeah,
did
I
you
did.
what the heck?
Yeah, thank you.
Yeah. Mhm. Hydrogenation of alkene. X, yep. Regioselectivity, stereoselectivity, syn and anti-addition, carbocation rearrangement, other nucleophile solution, water, alcohol, intermolecular isomerization. Okay, yeah. So looks like he stopped before isomerization, but you already know about that because I remember you asking me that question before. So dehydration. I see 3 different reactions that you went over here, and I'll give that 3 like this. 1, 2, 3. And then the second reaction you went over, there's like 2 parts. But yeah, I'll give you part A and part B for 2. Say this is A, which is going to be oh, and we react this with HCl. And part B is going to be like this right here. So let me make this like that there. So then, yeah, there we go. This with HBr. C. Oh no, number 3. There's gonna be 2 parts as well. This is A. H2SO4 water. I see 3 parts. I see 3 things here. H2SO4, CH3OH, and one more thing here. Whoa. Okay, so this is going to be 1, 2, 3, 4, 5, 6 problems total. Take a screenshot of this, Elysia, try them out, and then I will check your answer afterwards. And don't worry if you get stuck on some, just skip to the next one, and then I could walk through the ones you are stuck with when I go over these answers with you. Okay. And Madison wanted to go over how to draw the major products for elimination reactions of alcohols. And thank you for sending me this practice problem.
I think, did the picture go through?
Yes, it
Okay.
did.
Okay, cool.
Yeah. Okay. Okay. Elysia, are you okay with these problems?
Yes.
Okay.
Thank you.
Yeah. Now, let me. down. The problem CH3 is CH2, C, H, OH. This is not bond line form. This is some other thing. I forgot what's it called. Not condensed formula. It's like Lewis structure. Or Kikuli.
Yes.
Kikuli. I don't like Kikuli structure.
Super annoying. Makes it
Yes,
complicated.
I know. Like a lot of professors, they tend to write it in Kikuli structure, in a problem. But luckily, not Helix. But I heard Bio does that too, right? Why like this? Does Bio write things in Kikuli structure and then he expects you to know it in one line?
I think so a little bit, yeah.
Yeah, I see. Wait, what the heck happened? Mhm. Okay. So the first thing I would do is convert this Kikuli structure into bond line form. So can you describe to me what this Kikuli structure would look like in bond line form?
Wouldn't it be like a cyclohexane?
Cyclohexane, that would be if we had a ring. In this case, we would not have a ring. Think of it as a linear branch. Wait, can you guys still see my screen? I don't see my iPad screen on my computer for some reason.
It's not there anymore.
Oh, it's not there anymore?
It
Okay,
was
okay.
there for a second.
Yeah. I thought there was something wrong with my my computer. There we go. Okay, there we go. So this would not be a cyclo like propane, butane, pentane, or hexane because we don't see a ring here. If we had a cyclo or a cyclic structure, like let's say cyclopentane, our Kikuli structure would look something like this. For cyclopentane, for cyclohexane, it would look like this, where we can visibly see the ring in the molecule. But in this case, we do not see the ring, so this is going to be a linear chain, right? So if we start at this left side of the molecule here, the CH3, that's going to be that carbon. This CH2 here is going to be that CH2 with two hydrogens like that. This C here is going to be that C with an alcohol and one hydrogen that's invisible. And this C here is going to be attached to this C that is attached to two methyl groups. And I'm going to draw those two methyl groups out like this and like that, right? So this curly arrow here is just showing me how I redraw this Kikuli structure into this bond line form here. All the hydrogens here are invisible, and all the carbons here are these points or vertexes of the bond line form. And the alcohol OH is this OH right here. Where the hydrogen of the OH is not invisible, we have to draw that out. And we also have to draw out the hydrogen of carboxylic acids, aldehydes, the major functional groups. But we could leave the hydrogens of alkyl groups invisible or implied, right? And because carbon has the fourth column, it wants to have 4 bonds to be neutral. So this carbon here, we can visibly see 1 bond right now. That means that this carbon here has 3 invisible hydrogens attached to it to fulfill the octet row. Right? Did that make sense on how we got to this bond line form here?
Yes, it makes a lot more sense.
Yeah. So now once you have the bond line form, we then see what functional group is present in this reactant, which is going to be this alcohol here. But more specifically, this is a secondary alcohol because this carbon here is attached to 2 other carbons. 1, 2. There's going to be 3 different types of alcohols: primary, secondary, tertiary. Primary alcohol would look like that, secondary alcohol would look like that, and then a tertiary alcohol would look like this. And that's because if you look at the carbon directly attached to the alcohol, and you see how many other carbons it's attached to, that's how we determine what type of alcohol it is. Primary, that carbon is attached to 1 other carbon. Secondary, this carbon is attached to 2 other carbons. Tertiary, this carbon is attached to 3 other carbons. Now, that would be important later on when we like do more alcohol reactions with like HX, like hydrohalogenation, like what I showed Wiley earlier. But once we have this alcohol here, we then see what do we have in the reagent, which is sulfuric acid. And this is a strong acid. Strong acid. Okay. And we only see H2SO4 by itself. No product solvent, meaning there's no water, H2O, or alcohol, ROH. So we don't have to worry about SN1 reactions here. Right. So if you just see H2SO4 by itself alone, then this is a big sign that this is going to be an E1-like mechanism, elimination reaction, like you said, elimination. And all elimination reactions, they would produce alkenes, double bonds. So I'm going to draw out the H2SO4 out like this, where our most basic atom here is going to be this oxygen of the alcohol. So we're going to protonate that alcohol. This oxygen of the alcohol is going to grab that hydrogen and then kick out that conjugate base, HSO4 minus. When we do that, this oxygen would now have two hydrogens. Right before it only had one hydrogen, but now it has two hydrogens. Do you know what the formal charge of this oxygen would be when it gains that hydrogen? It might be easier if I drew it out like this. Like, what would be the formal charge of this oxygen here?
Isn't it positive?
+1, yes. So we turned a neutral functional group into a positively charged functional group. And this right here is what we call an oxonium ion. Right. And this is a good leaving group. Have you heard about that term before, the leaving group term?
Yes, but
Yes.
I feel like I need refreshers on all that. But
Yeah.
understand, yeah.
Yeah, right. When was the last time you took 8A?
I did it in community college probably this
Mm.
time last year. So it's been like a year.
Oh, like winter 2024, like at a community college. So not even Davis 8A.
Yeah.
Oh my gosh.
I know, it's different.
Yeah. And it's been like a whole year too.
Yeah.
So a good leaving group, you could think of it as, so a leaving group is going to be a group that leaves with a negative charge. Not a negative charge, but group that leaves with a pair of electrons. That's the more accurate thing to say, pair of electrons, because not all leaving groups will leave with a negative charge. Some leaving groups will leave and become stable, which is this leaving group right here. Right. And a good leaving group is going to be a leaving group, which is a group that leaves with a pair of electrons that can stabilize that pair of electrons, stabilize the pair of electrons. So for example, because we know this oxonium ion here is a good leaving group, let me highlight that instead. Yeah, this is a good leaving group. And I'll show you why this is a good leaving group. We're now going to think of this as an SN1E1-like mechanism. For those mechanisms, the first step is always going to kick out the leaving group by itself. So once we have that oxonium ion, this bond right here, attaching this carbon and oxygen together, represents 2 electrons. I'm going to break that bond and move those 2 electrons out onto the oxygen right there, kicking out that leaving group. Right, we're making the leaving group leave the molecule now. So as a result, our intermediate would look like this, plus this group that just left. And before, we saw this oxygen here had 1 pair of electrons. But when we kicked it out, we gave it an extra pair of electrons from this bond right here, which is why this oxygen now has 2 pairs of electrons, 2 bonds, and its formal charge is now 0, making it neutral. And would you say this neutral molecule here is stable or unstable?
Isn't that unstable?
So unstable would be something that is reactive, a lot of energy, negatively charged, positively charged. But this overall molecule here is neutral. Think of it as neutral H2O, right? And this is H2O here, right? We have two hydrogens and oxygen, and we have no formal charges at all. Like we have no negative charge, no formal charge. So this is stable. This neutral water molecule is stable.
Okay, that makes sense.
Mm-hmm. And because this is a stable molecule, because it's neutral, no formal charges, all the octet rules are satisfied, fulfilled. This is a very happy molecule, making it stable, which makes it less reactive, aka less energy, right? So this is important to know for conceptual questions, especially for Levens, because she will have a lot of vocabulary questions on her quizzes. And ranking questions, if she tells you to determine which molecule is more stable versus which molecule has like more energy, that's different because stability and energy are inversely related. The more stable a molecule is, the less energy they have. They're inversely related. You could think of it as like if the molecule is happy and stable, it is not going to be angry. It's not going to have a lot of energy. But if the molecule is very angry and unstable, that means that that's going to have a lot of energy. That molecule is going to have a lot of energy if the molecule is unstable. Right. And because it is less reactive, it's going to be happy as it is. So this is a good leaving group, right? Because it's going to stay as is when we kick it out, making it a good leaving group. If it was a bad leaving group, that means that this leaving group here that just left would be extremely unstable, making it highly reactive, highly energetic, which means that it's going to want it to come back and attack and go back to where it was before. And that's a bad leaving group because it's extremely reactive when we kick it out. But when we kick this group out, it's stable, making it a good leaving group. Okay, so that's the definition of leaving group and what makes a leaving group a good leaving group versus a bad leaving group. Now, before, if you look at this carbon here, this carbon had 4 bonds. I'm just drawing out that hydrogen explicitly to show that this carbon here had 4 bonds. 1, 2, 3, 4. When we kicked out this good leaving group here, this carbon now has 3 bonds. Right? I'm just going to draw out that hydrogen to make it clear where the 3 bonds are. This carbon here has 3 bonds. 1, 2, 3. And the formal charge of this carbon would therefore be +1, right? Because carbon is on the 4th column of the periodic table, meaning that it wants to have 4 electrons to itself. But when it lost a bond, it only has 3 bonds to itself now. So 4 minus 3, +1, right? And when you have a positively charged carbon right here, that intermediate is called a carbocation intermediate. Carbocation intermediate, right? Do you remember what step we have to look out for after we form any sort of carbocation intermediate? It's okay if you don't remember because it's been like a whole year, but do you know what would be next after we form this carbocation intermediate, like what you look out for?
Not really.
That's okay. So the next thing we look out for is carbocation rearrangement, like to see if we can make it more stable. So let's go over the different stability types of carbocations. This is a methyl carbocation. This is a primary carbocation. This is a secondary carbocation. And then this is a tertiary carbocation. We won't worry about resonance for now because actually in 8B, you did go over that. So let me just go show you this here. Say that. Okay. So this is a methyl carbocation. This is a primary carbocation, secondary, tertiary, and this is a secondary allylic carbocation. this right here at the left side is a methyl carbocation because this positively charged carbon is a methyl group, part of a methyl group. There's no R groups attached to it. The primary carbocation only has one R group attached to it. Secondary carbocation has 2 R groups, tertiary has 3. And we'll worry about the secondary allylic later. But the more substituted the carbocation is, the more stable it's going to be. So stability is going to increase from left to right. I mean, yeah, left to right in the way that I drew it here, right? If she asks you for what factor determines this, the correct answer would be hyperconjugation. Hyperconjugation, right? Which means that these R groups here donate electrons inductively to the carbocation, right? They're donating electrons, making this carbocation stable, right? Because opposite charges attract. Electrons are negatively charged, carbocations are positively charged. So when this carbocation has more R groups attached around it, it's supported by more electrons, more negatively charged. You could think of it as more friends. Like this carbocation here has the most friends around it, making it the most stable. Whereas this carbon here has no friends. There's no R groups attached to this carbocation. Hydrogens, they do not count as an R group. They cannot donate electrons inductively, right? But the hydrocarbons, they can. So the more R groups around the carbocation, the more stable it's going to be. But we see here, this carbocation is secondary because it's attached to 2 other R groups, 1, 2. But we see that this is allylic. Allylic meaning that it is 1 carbon away from an alkene like that, right? And this secondary allylic carbocation is going to be more stable than this tertiary carbocation, even though it has less R groups attached to it, because there's one more big factor here that is going to influence this stability. And that is going to be resonance. This alkene here can shift and pop onto that bond to give us this resonance structure here, right? Where we see that when we did that, this double bond here is now over here, which gave this carbon here that used to have the carbocation an extra bond, which is why that carbon is now neutral, formal charge of 0. But this carbon here lost a bond. Before it had 4 bonds, 1, 2, 3, 4. But when we shifted that double bond over, it now has 3 bonds, which is why it has the carbocation over here now. So we see that the positive charge here is delocalized. Delocalized meaning that it could move around, flow around the molecule more freely, has more breathing space, making it more stable. So resonance is a bigger factor than hyperconjugation, which is why the secondary allylic carbocation is more stable than the tertiary carbocation. This tertiary carbocation here cannot do resonance. It's not delocalized. It's stuck there, right? It's suffocated. Whereas this secondary allylic carbocation here, because it could do resonance with alkene, it has more breathing room. It could delocalize. It could move around more, making it more stable, even though initially it looks less stable because it has less friends, less R groups attached to it. Right? Did that carbocation stability make sense? Any questions on that?
That makes a lot of sense. No questions. You explain it so well. So
Yeah, I'm glad. Thank you.
yeah, of course.
Okay, so now once we understand the carbocation stability, we then see what type of carbocation we formed in the intermediate, which is a secondary carbocation. Then whenever you form this carbocation intermediate in any kind of mechanism, right? Whenever you do any kind of reaction and you form some kind of carbocation intermediate, you stop and look out for carbocation rearrangement, which is going to be like a hydride shift or a methyl shift. Hydride or let's say alkyl shift. Right? Once we know that this carbocation is secondary, we look to the right and left of it and see if it becomes more stable. To the left of it is another secondary carbon. To the right of it is another tertiary. It's a tertiary carbon. right? So this tertiary carbon right here can stabilize the positive charge better because it has more R groups attached to it. So we can actually shift this carbocation over, but do not draw this arrow here, right? Because when we draw arrow pushing mechanisms, they always start from electrons and they always go to an electron deficient area. So this is the wrong arrow, right? Positive charges would never move. Electrons will always move towards positive charges. So what we're going to do is we're going to draw out that invisible hydrogen that is attached to this tertiary carbon, and we're going to do a hydride shift. This bond right here with that hydrogen, which I'm going to highlight in yellow like this, the hydrogen and the bond, is going to shift and go onto that carbon right there that has the carbocation. Because this carbon right here is missing a bond, and we're giving it a bond by doing this hydride shift right here. So when we do that, this hydrogen here that is not highlighted is that hydrogen right there. It's always been there. But now when I did that hydride shift, this highlighted yellow hydrogen is now on this carbon. And we see that this carbon now has 4 bonds, 1, 2, 3, 4, satisfying the octet rule and making it neutral, formal charge of 0. Positive charge is no longer there. But if we look at this carbon over here, before it had 4 bonds, 1, 2, 3, 4, after the hydride shift, it no longer has that yellow hydrogen. So it lost a bond, giving it a positive charge. And that is favorable. We were able to do that because we were able to form the more stable carbocation intermediate, the tertiary carbocation.
That makes sense.
Once we have that tertiary carbocation, the next step, if we think about this in elimination type of reaction, E1 mechanism, then what we want to do is we want to label our alpha and beta carbons. So let me go over what alpha, beta carbons are. Let's say we have this carbocation here. And we have this chain. It's some random chain like that. The first carbon is going to be the alpha carbon. The second carbon away from the carbocation is going to be the beta carbon. And then the third is going to be gamma, fourth delta, fifth epsilon, and so on and so forth with the Greek alphabet. It doesn't have to be in terms of a carbocation. It could also be in terms of alkene or a carbonyl, carbon of 1 oxygen. If we look at this alkene right here, these are the alkene carbons. Don't label alpha, beta there. The first carbon coming off of that alkene are these alpha carbons right here, because these carbons are the first carbons coming off of that alkene. And then this right here would be the beta carbon, because that's the second carbon coming out of the alkene. Same as this carbonyl, right? A carbonyl, whenever you see or hear carbonyl, that represents a carbon double bond oxygen, which is this carbonyl here. And there's a lot of carbonyls that you'll see. There's aldehyde, there's carboxylic acid, there's esters, there's amides, there's acyl-halide, there's anhydride, right? There's many carbonyls that you have, right? Because all of these functional groups has a carbon double bond oxygen, which is a carbonyl. If this is the carbonyl carbon here, this is going to be the alpha carbon, this is going to be the beta carbon, and this is the gamma carbon, like that. Okay, so let's go back to the carbocation case. So this right here is my alpha carbon. These are my beta carbons right here. Right. So I'm going to draw out at least 1 beta hydrogen for each beta carbon in red. This is a beta hydrogen. This is a beta hydrogen. And I'm going to say this is a beta hydrogen right here. Right. Before we move on to the next part, let's go over alkene stability. So let's say we have this alkene, that alkene, this alkene, this alkene, this alkene, this alkene, and then this alkene right here. Stability is going to increase from left to right. And the differences between them are going to be how substituted they are. This is an unsubstituted alkene because there are no R groups attached to that alkene. This is a mono-substituted alkene because there's one R group attached to this alkene. All of these three alkenes here are di-substituted alkenes because there's two substituents attached to the alkene. This is a tri-substituted alkene because three R groups are attached to the alkene. And then the most stable alkene is a tetra-substituted alkene because there's four R groups attached to the alkene right there. So the more substituted the alkene is, the more stable it's going to be, like a carbocation. The more substituted the carbocation is, the more stable it's going to be. So if we think of this in terms of the stability arrows, these are going to be the arrows here, where I'm going to look at the di-substituted ones more closely because this one here is a trans alkene, this is a cis alkene, and this is a geminal alkene, right? For trans alkene, the two R groups are on opposite carbons of the alkene, different carbons, and they are on the opposite side of each other in reference to the alkene line, right? This R group here is on this side of the line, this R group here is on the other side of that line. But for cis alkene, those two R groups are on the same side of the line, right? Both of these R groups here are on this side of the line. But geminal, the two R groups are on the same carbon, right? For cis and trans, those two R groups were on opposite carbons, like that, opposite carbons. But geminal, the two R groups are going to be coming off of the same carbon, not opposite carbons. And geminal and cis alkenes are going to be similar in stability, right? Cis and geminal, there's like they're the same stability. Okay. She asked why. The reason is going to be steric hindrance, right? Which is how molecules bump into each other. If you see these two R groups right here, those two R groups will bump into each other, causing steric hindrance. These two R groups here will cause steric hindrance, bumping into each other. And we don't want that. That bumping effect is steric hindrance, and that is unstable. That's a destabilizing factor. But when we look at the R groups of the trans alkene, those R groups are facing away from each other, avoiding each other, not bumping each other, reducing steric hindrance, making it more stable, which is why the trans alkene is more stable than the cis and geminal alkene. Okay. So now, if we go back up here, and we want to make the more stable alkene, we have to look for which hydrogen is more substituted, right? And we're going to focus on these red hydrogens here, all these beta hydrogens here. The one on the top is primary because this carbon here is attached to only one other carbon. This is also primary because this carbon here is attached to one other carbon. And then this carbon here is secondary, right? Because this carbon, this beta carbon, is attached to two other carbons, 1, 2. So we are going to be interested in this hydrogen here. We're interested in that hydrogen because it's the most substituted hydrogen, which will lead us to the most substituted alkene. Okay. So the next step here is to bring in the conjugate base, HSO4 minus. You could write it like this, which if it makes more sense, then I would recommend doing it like that. But I'm gonna do it like this to accurately show like the negative charge on that oxygen right there. That's gonna be my base, which is going to grab that beta hydrogen. And then when this HSO4 minus here is grabbing that hydrogen, this bond here with 2 electrons is going to go to make a double bond right there. Right, and we can do that because we're giving this carbon here an extra bond by creating a double bond right there. And when we create this double bond right here, this carbon will maintain its 4 bonds, right? Because we're getting rid of this bond and then adding that bond right there. So right now it's kind of messy, it's all over the place, but I'm gonna like redraw the mechanism more clearly after this, because right now I'm just like annotating all over the place. So then I like explain to you each small little detail for it to make sense. Because if I just like go straight into the mechanism without explaining those details, you might get lost, right? But right now, is it making sense, or are there any like details that you are like not understanding right now?
No,
Right,
it makes sense. It's just putting it all together.
yeah. Okay. But that would be the result, and let me put it all together now to make it more clear, right? Because like right now it's like all like annotated. Right.
No, I totally see. I get what you mean. Now it all
Uh,
makes sense. Oh my gosh, thank you so much for explaining that. There's so many parts.
yeah, I know, I know. There is a lot of parts to this mechanism, and especially do you like recognize any of these terms like steric hindrance, resonance, substitution when you take OChem? Uh,
Yeah, I recognize all of the terms. It's just like some of them I like remember more than others, if that makes
uh-huh.
sense. But it's like
Right.
remembering all the details about all of them. So
Yeah, we want all the
having that
details about them.
refresher is so like helping.
Yes, that's good. And for 8B, you don't need to know all of the details from 8A. You just need to know the important ones. But that's like going to show up as you learn about them. And I'll also tell you like what you need to know, and you don't have to worry about any other 8A concept. Just like send me your lecture notes and practice problems, and then I can just teach you from there. And you don't have to worry about like all the other like previous content.
Wow, okay.
Right. Uh-huh.
Sounds good. Thank you
Yeah.
so much. I don't want to take
Mhm.
anyone else's
Yeah,
time.
yeah. No worries. I'll probably like write out this mechanism like in detail like tomorrow's office hours. Right.
Okay, sounds
Yeah.
great. Thank
Mhm.
you.
Yeah, no worries. Well, this is already the mechanism in detail, but what I meant was like draw the mechanism more cleanly, like in less detail, but more visually like understanding.
Yes, yes, thank you.
Yes. Uh-huh. Yeah. Okay. Hey Elysia, were you able to do these problems that I gave you?
I got I think like 4 of them. I
Mm-hmm.
was kind of stuck on a few.
Yes. What were the 4 that you got so far?
I went over 1,
Mhm.
2B, 3A, and
Mhm.
3B.
Okay. Let's start with 1. What does your product look like for 1?
I got 2 products which are like racemic.
Yes.
Um,
That's correct.
so I ended up getting like basically one had like hydrogens on 2 wedges, and the
Mm-hmm.
other one was hydrogens on 2 dashes. And
Mm-hmm.
then I kind of emphasized the like the the wedge and the dash on the ethyl.
Mm-hmm. Right? If the hydrogens were wedges, then the ethyl and methyls would be dashes. If the hydrogens were dashes, the ethyls and methyls would be wedges, like that.
Yeah.
And that's good. You got it. That's correct.
Yay.
The most important thing here is probably the syn addition part of this,
Yeah.
right? And this would give you full credit, but you could also do plus minus here to show that you get the enantiomer version of that. But to be safe, I would do it in this way like you did, because there might be what problem can you think of that would not work? Like this sign would not work here.
Um,
Right.
would it be if we had like dashes and wedges assigned already and like um it wasn't
Part of the
anti?
alkene. So yes, if we had wedges and dashes already that are pre-existing, that is not part of the alkene or not reacting at all. Like let's say this wedge methyl here, we see that nothing touches that carbon. Nothing touches that carbon at all. So it stays as a wedge. And if that's the case, would these be enantiomers or diastereomers of each other?
Um, Diastereomers?
Diastereomers, right? Because the carbon here is going to stay as a wedge. That's the same stereochemistry. But the
Right.
carbons here change because those are the carbons of the alkene that is reacting with the H2. So some chiral centers change, some chiral centers stay the same. That would make it diastereomers. So we cannot use that plus enantiomer or plus minus symbol that Helix does. If there was a pre-existing chiral center somewhere else that is not going to change, that is not going to react.
Right.
Mhm. But in this case, there were no other pre-existing chiral centers, so you could have just put plus minus, doesn't matter. But that's why I'm saying it's safe to, just invert the stereochemistry at the carbon that reacts which are these alkene carbons here.
Right.
Mhm.
Which is what we talked about yesterday.
Yep, right. 2A, what did your product look like for 2A?
I was a bit stuck because I think I was learning that if there was like a carbocation like right next to something that is like that could be joined as a ring, I was kind of like stuck there.
Intermolecular reaction, you're thinking of that, right?
Yeah.
Yeah. So that I'm gonna tell you is gonna be one of these problems here that you have to make a ring intermolecularly.
Mhm.
So let's think about this mechanistically first. When we have an alkene and a strong acid here, what do you think is gonna happen between them?
Well, the alkene is gonna want to grab the hydrogen, and then the bond between the hydrogen and chlorine, there's another arrow drawn toward the chlorine, so it kicks it off.
Right. The alkene is gonna grab that hydrogen, but there's two carbons that could grab that hydrogen. Which carbon do you want to grab this hydrogen here?
I know I want the carbocation to be the one on the left side.
Yep, we want the carbocation there, meaning that we want that carbon to lose a bond, right? And if we want that
Yeah.
carbon to lose a bond, that means the other carbon, this carbon here, is the one that's gonna grab that hydrogen in order for this carbon to lose a bond and have that carbocation right there.
Right. Okay.
So the less subcarbon is going to grab that hydrogen, kick out that chlorine to give us this carbocation intermediate here. Because this carbon lost a bond, this carbon here still has 4 bonds, so no charge there. And whenever we have this carbocation intermediate, we stop, we look out for hydride shift or methyl shift. But in this case, we don't
It's
have to
on
worry about that.
the more preferred position anyways.
Yes, correct. It's already on the most substituted position, the tertiary position, making it the more
Yeah.
stable carbocation. So we don't have to worry about that because this one here is secondary, this one here is secondary, this one's here secondary. They are worse carbocations positions than this tertiary one. So we don't have to do any hydride shifts here. So once we have this carbocation right here, the Cl minus that got kicked out is gonna float around and
then get the carbocation.
yep, hit the carbocation, attack that. And in this case, I want to emphasize the stereochemistry here. So I'm gonna add let's see here. I'm gonna add what am I gonna add? An isopropyl group right there, like that. Right. I'm gonna add isopropyl group here, just so we could include wedges and dashes.
Okay.
Right. Okay. So what is the stereochemistry of this? When the chlorine attacks, what kind of bond would it be? A wedge or a dash, or would it be both? Think about the geometry of this carbon and its hybridization.
I would think it would. I would think both.
Both, right? It is because this.
Because it has I was gonna say my reason would be that it has 4 different bonds attached, or like 4 or 3 different things attached.
Right now, yes, 3 different bonds attached to it. And what would be its hybridization if it has 3 different bonding groups? Would it be sp, sp2, or sp3?
SP2.
Yes, sp2. And do you remember the shape of that? Like, would it be linear, flat, and planar? Would it be tetrahedral?
Planar.
Planar, yes, flat and planar. And because it's flat and planar, when the Cl minus comes into attack, it could attack on the top side, giving you a wedge chlorine, or it could attack on the bottom side, giving you a dash chlorine. Doesn't matter. It's 50-50 chance in this case, right? Doesn't matter. 50% chance. So
Right.
let's say it's a wedge. That would make this isopropyl group here, dash. It could have been the other way as well. This chlorine here could have been a dash chlorine, and this isopropyl group here could have been a wedge, like that.
Right.
And would this be enantiomers or disomers of each other?
It would be enantiomers.
Yes, enantiomers, because one chiral center here, that's only one we have in this molecule, changes, and that means all of the chiral centers changes, making them enantiomers of each other.
Right.
You got it. And that would be a racemic mixture, because we'd get 50% of this enantiomer, 50% of that racemic mixture. Okay. So in this case, we didn't have to worry about that, but let's do 3C here. And then for the other ones, I'll check your work for tomorrow's office hours. I agree
Okay.
have to work on this for tomorrow. But let's do 3C here.
Okay. Okay, I didn't end up doing 3C, but I could walk through the process.
Yes, walk me through the process.
Okay. So I think the first step would be for the alkene to attack the H2SO4, grab the hydrogen.
Which part of the alkene?
I want to say the right,
This one?
or that one forms the carbocation, so the
Yes.
other one.
Yes, the right one would form the carbocation,
Yeah.
making the other carbon grab the hydrogen, forming the carbocation on the more subposition.
Right.
Okay.
And then after that, we have
There's no water or alcohol here, so we can't use that to attack this. But there is a water or alcohol somewhere in the original reactant molecule.
Yeah. I want to say the OH and
Right.
the carbocation are gonna join together.
Yep.
And then it's gonna form like that ring.
Yes. That right there is an intramolecular reaction, because this alcohol oxygen here, the nucleophile, is on the same molecule as this carbocation here, the electrophile. And whenever the
Yeah.
nucleophile and electrophile are on the same molecule attacking itself, you could say, like this molecule is attacking itself, like one part of the molecule is attacking another part of itself, the same molecule, that's going to be an intramolecular reaction. And all intramolecular reactions, there's going to be different types that you learned. This is one of them. The first one you learned was like Williamson ether synthesis. There's one type of intramolecular reaction there. All intramolecular reactions will always form a ring. Always forms a ring. And a lot of students get confused on how many membered ring is it going to be, like how big the ring is going to be. But what I like to do is I like to start my number one atom. I like to start numbering. I'm going to start my number one atom at the nucleophile, and then I will go all the way until I hit my electrophile right there. And that tells me how many members are going to be on the ring, how many atoms are there going to be in the ring, which in this case, 6. 6 atoms in the ring, but not all 6 atoms are carbons, right? Because the way that I numbered it, the first atom is an oxygen atom. So
is there a reason like why you're able to do that?
Why I am numbering this oxygen here number 1?
Yeah, or is it just like to make sure that you're counting the amount of bonds that you have so you can join them as 6?
Yes, it's just to count the number of atoms to make sure that we have 6 atoms in the ring. And the reason why I'm starting at the nucleophile and ending at the electrophile is because we're, like you said earlier, we're joining these 2 atoms together. We're connecting those 2 atoms together. Because right now, you see how 1 and 6 are not connected? Like there's no bond between 1 and 6 at all. We're making that bond from this arrow right here, because this arrow is starting from this pair of electrons, and that pair of electrons is going to make a bond between atom 1 and atom 6. We're connecting 1 and 6 like that, which makes the ring. So you can think of it, this oxygen here is going to connect to that atom 6, and this right here is the ring, but that's an ugly ring. We're going to redraw it, right? So we know that the ring is going to be a 6-membered ring, where one of the atoms of the ring is oxygen. So I'm just going to draw that oxygen somewhere like this. right? When that's my atom 1. And I'm going to draw my template out like this, which is that 6-membered ring where one of the atoms in the ring is an oxygen, like that.
Right.
And I know that oxygen is number 1 as I numbered it, and I'm just going to number it randomly. 1, 2, 3, 4, 5, 6. You could have gone the other direction as well. It doesn't matter. Like you could have gone counterclockwise. What matters is what is attached to these atoms, right? This right here, which I'm going to highlight in yellow, the numbered atoms, is the backbone of the ring, which is this backbone of the ring right here, the 1, 2, 3, 4, 5, 6, like that. Right. Now, what is attached to each of these atoms? That's the decoration. You could think of that as like the fluff, the decoration of this mechanism.
Mm-hmm.
So at atom 2, we see an ethyl group attached to it. And I'm going to add that ethyl group like that. At atom 6, I see 2 methyl groups, 1, 2. So I'm going to add 2 methyl groups at atom 6, like this. 1, 2. At atom 1, the oxygen, it is attached to this hydrogen right here still. So I'm going to explicitly draw out that bond to its hydrogen that it's still bonded to. Right? Before it had 2 pairs of electrons, but now it has 1 pair of electrons. Because it used one of its pairs of electrons here to make this new bond here between atom 1 and atom 6. This right here is new. Before, that bond was not there between 1 and 6. But we made that bond from this pair of electrons right here, which makes that new bond right there. Right. So
Okay.
now what would be the formal charge of this oxygen here with 3 bonds and 1 pair of electrons?
You said the oxygen?
Yeah.
I think it would have a plus.
Yes, plus charge. 6 column. It has 1, 2, 3, 4, 5 electrons itself. 6 minus 5 plus 1. So we don't stop here because we want to get rid of that plus charge to make it stable and neutral.
Yeah, so then we would have the HSO4
HSO4 minus. Yep.
and then I would grab the hydrogen, and then that bond between oxygen and hydrogen from the ring would kick off the oxygen.
Yes.
And then make it a neutral charge and stable.
Yeah. And that creates our final cyclic structure.
Yay!
Yes. That's good.
That wasn't too bad.
That's good. That's
So
good.
so in these cases, when we know like there's like a potential ring that's going to form, we know it's going to be like there's like an not oxygen, an alcohol attached, and like an alkene ring, or
Yes.
like sorry, alkene.
Yeah. And an acid with nothing else, like no alcohol, no water there. You know that the alcohol or water is part of the molecule, so you know that a ring is going to be formed.
Okay.
Okay, this one here is going to be a little bit more tricky, but this is what I'm going to give you as homework, and then I'll check your answer at the end.
Okay.
I mean tomorrow. Yeah, tomorrow's office hours.
Okay.
4, 5.
And then I'll try to submit it into the file.
Oh yes,
just so
you're
you
right.
have it.
Yes. That's good. Like that. Okay, yeah. This is the final one here, with H2SO4 as the reagent. That's good. Yeah. 1, 2, 3. Okay. That's good.
Okay. Let me take a screenshot. Okay. Thank you.
Yep. No problem. And Wiley, when you have your bio lecture tomorrow, after your class, can you send me the notes so that I could prepare Microsoft times and then we could go through them in tomorrow's office hours as well?
Yeah, sure.
Yeah, and I think this link right here, like it kind of goes over what you're gonna go over because this one involved alcohols as well, how alcohols will act as nucleophiles and attack.
Okay.
Yeah. Okay. And Madison, I'll like when are your lectures, Madison, for 8B?
They are on Monday, Wednesday, and Fridays.
Monday, Wednesday, Friday. Oh, so you also have lecture tomorrow as well. Okay, so we
Yes,
could go over,
tomorrow, yeah.
what you will go over lecture tomorrow as well.
Okay, and then can I text you about like inquiring about private sessions and stuff?
Yes, you could text me about that, and I'll get back to you as soon as possible. Wait, right now, so far we've been texting on, I think, oh yeah, I think Jenna gave you my number, right?
Yes,
Yes,
yes.
yes, yes, yes.
It was actually last quarter, but I like ended up not being able to get into one of the labs, so I wasn't able to take it.
Oh, that was last quarter. I see. Right, right. Yeah. You
So
could text me.
I have your Instagram that I messaged you again on for this quarter just to make
Right.
sure.
Yes.
But yeah,
Yeah.
either one works.
Yep. Either one
Okay.
works. Either one would work.
Okay, perfect. I will do that then.
Yes.
Thank
Yeah.
you so much.
No, no worries. Okay. I'll see you guys tomorrow. Good night. Good night.
Bye, good night.
Bye.